In this video, we're going to talk about Newton's law of cooling. But before we do that, I need something to cool, and I also really need some caffeine, so I think we can solve both those problems.
I'll also note that the ambient temperature of my house is set at 20 degrees Celsius.
So before I even get into the video, I'm just going to record the fact that that ambient temperature, I'm going to write that down as A, was 20 degrees Celsius, and I'm actually going to convert that to being 68 degrees Fahrenheit, just because the thermometer you're going to see in a moment is going to be in Fahrenheit as well. All right, so I've got my tea, but I now want to figure out exactly how hot is it.
And that's looking about 161 degrees.
So I'll write that down, and I have that the temperature, which I'll denote by T at time T equal to 0, was 161 degrees Fahrenheit. And I'm actually going to collect one more piece of data in 2 minutes. I'll have a temperature at time T equal to 2, and I'm going to come and fill that in when I have it. All right, so now I want to model this scenario, and we're going to use a separable differential equation. So why do I want to use a differential equation to model this? Well, differential equations are great when you can say something about the rate of change. And often the rate of change of a quantity is easier to say something about than the quantity itself. So what kind of differential equation should I write? I'm going to try to study the change in the temperature with respect to time. The change in capital T is temperature and lowercase t is time. I know that's just annoying. And the idea is this is going to be proportional, so I'll write some constant of proportionality, to something. But what should that something be? Well, when we were studying exponential growth, like for example, the spread of a pandemic, you'd say the rate of change is proportional to how many people are infected. So the rate of change was proportional just to the number, to the quantity of the variable that we were studying at that time. But now that doesn't seem quite as reasonable. For example, if the temperature in my cup is very close to the ambient temperature, I wouldn't expect a very rapid change. But if the temperature was way above the ambient temperature, you might expect a rapid change. So indeed, I'm going to say this is proportional to the difference between the temperature of my mug, between my cup of tea, and the ambient temperature. So I will model it as K times the temperature of my mug minus the ambient temperature. And then is this plus or minus? Okay, T is bigger than A because the temperature of my cup is hotter than my ambient temperature. So that's positive. And then when it's hotter, it should be cooling. The rate of change should be going down. It should be a negative, so I'll put a negative there. That is my model for this scenario. All right, so 2 minutes is up. Now let's try measuring it one more time.
And looks like we're at 153.7, just a little over 2 minutes later.
Okay, so I'll just record that observation. This was about 153 degrees Fahrenheit. That's what happened at time T equal to 2. Set timer for 5 minutes. Okay, so let's go and solve this. The first thing to observe is that this is a so-called separable differential equation. There's a portion on the right here that only depends on the temperature. And there's also a portion here, well, in fact, there's no portion that depends on time, but I'll say the portion that depends on time is just this constant function, the minus k. And so what I do is I separate my variables. On the left-hand side, I'll write everything to do with the temperature. So that had a dt. And then I'll also have the 1 over t minus a. And on the right-hand side, I'm going to have my minus k and my dt. So I completely separated the lowercase t and the uppercase t. And then I'm going to do an integral on both sides. And the details of this methodology of separation of variables we've covered in the previous video in this course. Now it's an integration problem. On the left, this is going to be equal to the logarithm of t minus a. I don't have to worry about absolute values at all because, well, it's a positive quantity. On the right-hand side, I have my negative. K becomes kt, and then I cannot forget that whenever you integrate indefinitely, you have this constant of integration, so I put my plus c down. Okay, so that is a solution, but I can do better. I can solve for big T. I have a logarithm on both sides, so let me take e to the power of the logarithm and e to the power of minus kt plus c. On the left, I observe that logarithm and exponential are inverse functions of each other, and thus these are going to cancel and become t minus a. On the right-hand side, I have the e to the minus kt, but how should I deal with that plus c? The plus c is an exponent. So it can come out as e to the c, it would then be a multiplicative constant. The multiplicative constant e to the c, but c is just some constant, e to the c is just some constant. Why don't I relabel it and call it a new constant, d? It just looks a little bit simpler this way. Okay, so I have an a I need to figure out, I have a d I need to figure out, and I have a k I need to figure out. 3 different constants. One of them I already know. One of them was the ambient temperature, and that was that 68 degrees Fahrenheit that we computed. To figure out the d, I could plug in the initial condition that we'd seen at the beginning, that T of 0 was 161 degrees Fahrenheit. So let me try that. T of 0 was 161 minus 68 is equal to d times e to the k times 0. I don't know what k is, but it doesn't matter, it's multiplied by 0. And e to the 0, in fact, I can even erase it because it's just equal to 1. So now I know that this d here is equal to, well, 93. Okay, so I've got the a, I've got the d, but what about the k? Well, the k was the reason I took the second measurement, where I took the temperature at the value of 2 and got this 153. The issue is that because the k was multiplied by t, if you just plug in t equal to 0, you'll never figure out what the k was. So I need to have a different point, a non-zero point. Well, let's now try to do that. If this first computation was done at t equal to 0, I'll now do a computation at t equal to 2. What do I get? On the left is 153.7 minus the 68. And then on the right, I now know the value of d, so I can put it in, the 93. And then it's going to be e to the minus k times the value of 2. So that's 85.7 on the left, but how do I even get to the k? I'm going to have to do some sort of logarithm. So to solve this, I'm going to say that 85.7 divided out, in fact, by the 93 is equal to e to the minus k times 2. Then I'll take my logarithm. So logarithm of 85.7, these are all such funny numbers, divided by 93 is equal to minus k times 2. And in fact, I'll take that 2 out from the right-hand side and divide it out on the left. That is going to be my formula. This is much too complicated for me to do in my head, so I'm going to go to the calculator. And the calculator tells me that k is equal to 0.0409. I suppose that's enough decimal places. And so what's our final answer? Well, we have our description of our problem here. I have my a on the left. I'm actually going to move it over to the right-hand side. And I'm going to get my final answer, which is the temperature function as a function of t, I'll make it explicit, is equal to the a first, a got moved to the other side, so 68, plus the value of the d, and the value of the d was 93, e to the negative 0.0409 times t. Note, by the way, that this k is not some universal property. It's about the geometry and the materials and the surface area of the mug of tea that I have. It's for my scenario, I get this value of k. If you have a different scenario, you'll have a different value of k. And so we have this model, and that can seem actually quite nice. This is sort of our solution. But how good is it? So I want to collect one more data point, and I did it 5 minutes later.
And now I'm all the way down to 142.7.
So this new data point thus is T of 7 is equal to 142.7. Okay, so that's the experimental. Doesn't mean my model is going to match it at all. So now we're going to get the moment of truth. What happens if we use the model, the solution to that we have come up with? So now the T of 7, according to the model, is 68 plus 93 e to the negative 0.0409 times 7. Moment of truth, let's type it into the calculator. And this apparently is equal to 137.8. And so that is the model's prediction in comparison to the 142.7, which was our experimental. So this result is reasonable, maybe not excellent. We've definitely got a little bit of a difference, about 5 degrees here, but not completely terrible either. So then there's a bit of a question of, well, do we like this result? Do we not like this result? There might be, for example, some experimental improvements we could have done, like recording the data a little bit more accurately. I was off by at least 30 seconds on one of my time measurements. But ultimately, this leaves us with the question of, do we like this model or do we not like the model? Remember, a model is not right or wrong. I mean, no model you write down will ever capture every single interaction down to the quantum mechanical level, for example. It's going to approximate it in some level. And that's what we're doing with Newton's law here of cooling.